I don't know what they were using it for.
Let me introduce Ilias Diakon Nicolas, and he's an assistant professor in the University of Southern California. He's working on the interface between theoretical computer science and machine learning. And he's particularly interested in studying the trade-off between statistical efficiency, computation efficiency, and robustness. Before that, he actually has spent time in UC Berkeley and also University of Edinburgh, and he got his PhD in Columbia University. Yeah. He's going to talk about robustness today.
Thank you, Len. So, can you hear me in the back? What does it mean? Yes, no? Okay. So, so I'd like to thank the organizers for inviting me to talk at this workshop, and in particular, I'd like to thank Anoop, because his very good talk is going to make my job much easier. So what's the context here, okay, of the previous talk and this talk? So we have a learning problem, and there are a number of criteria, a number of resources we care about when we solve it. One of them is sample efficiency, the thing that statisticians have been looking at for like a century. Another is computational efficiency, what computer scientists have been focusing on. And the third one that has been to some extent sort of underrepresented is robustness. So usually we have a model in machine learning. You assume that you get some kind of samples from this model. And under this assumption, you want to efficiently learn. Now, what happens when these assumptions are not exactly true, but they're only approximately true in a well-defined sense? So the question is there so for high-dimensional problems, is there a trade-off between computational efficiency and robustness? Can we design algorithms that are provably robust and provably computationally efficient? So this has been an open problem for a long time, even for the most basic models, even for a single Gaussian. At the first approximation, at least, recent work has shown that the answer is no. There really is no trade-off, no inherent trade-off, and we can actually reconcile computational efficiency and robustness for these models. So this is joint work with a number of people. So Gautam Kamath, Daniel Kane, Jerry Lee, Ankur Moitra, and Alistair Stewart. So let me begin. So I'm going to have a long intro, similar to maybe even longer than Anoop. So this is maybe if you see it twice, you never need to see it again. So again, what's the setting? Okay, so the most basic statistics 101 parameter estimation setting, you get samples from a one-dimensional Gaussian, unknown mean, unknown variance. You want to learn it. You want to learn the parameters. It's straightforward to do this. Just take the empirical mean and the empirical variance. So these are the best possible estimators under these assumptions, which means that they are sample optimal, though the rate of convergence is as fast as it could be. And they're easy to easy to calculate. Now, these particular estimators, the empirical mean and the empirical variance, are a special case of a much more general framework, which is the maximum likelihood estimator of Fisher. Now, if it was 2005, so I'm a theoretical computer scientist, so what people were doing at that time was, okay, the maximum likelihood estimator is what you would like to be able to compute, but for complicated models like mixtures of Gaussian, it seems that it is hard to compute. So what can we do to get something similar to what the MLE does, but do it with a computationally efficient algorithm? And there were a bunch of papers doing great theory work on this topic. So this is not one of these talks. So we're considering a setting where the maximum likelihood estimator is the wrong thing to do. Even if you use infinitely many samples and infinite time, it's going to converge to the wrong answer. And the reason for that is that the assumption about the samples coming from the model is not going to be exactly true. So this is a question that Tsuki asked in the 60s. So what happens when the model is misspecified? So I'm going to define everything very soon. Okay, so this is an area of statistics. It has developed more or less independently from many sort of other areas within statistics and computer science. There are books and conferences every year. So this is the generic question that they ask. So can we design estimators that are stable so they behave well in the neighborhood of a model? So the simplest possible example is learning a corrupted one-dimensional Gaussian. So you'll see some overlap in the slides, in the introductory slides. This is not a coincidence. Okay, so here is the ideal model, so a Gaussian with unknown mean and variance. We add some noise to it, and this is the observed model. So these pictures, they actually represent the probability density functions of the underlying one-dimensional distributions. So this is the observed model. So this is the PDF of the distribution that you obtain samples from. So what do we do to estimate the parameters of the green of the observed model? To answer that, I need to define the precise noise model. Okay, so there are two ways to do this informally. One thing is to say that the L1 norm of the noise is going to be at most epsilon for some parameter epsilon, or that the total variation distance, or L1 distance, between the ideal model and the observed model is going to be at most epsilon. So I'm not going to insist on constants for this talk. So whenever there is a big O, it's some universal hidden constant that we won't care about too much. OK, so now this noise model, where we get samples from a distribution which is epsilon close in L1 to a good distribution, a distribution in the family, is a generalization of Huber's contamination model. So Huber's contamination model is the classical model in robust statistics, and it prescribes that the noisy distribution, the observed distribution, which is the green thing here, is going to be obtained as a mixture with weight 1 minus epsilon from the ideal model, and with weight epsilon from a fixed but arbitrary noise distribution. And in terms of approximating the underlying distribution, we need to have some kind of definition. So the previous talk focused on estimating the mean vector up to Euclidean distance and the covariance matrix up to Frobenius norm. This is the reasonable thing to do for many models. So we'd like to use a slightly more general type of error metric that does not sort of depend so much on the particular model that you look at. So in particular, we're going to use the total variation distance. So what we really want to do is find parameters for our hypothesis such that the total variation distance between the true distribution and the unknown distribution is going to be O of epsilon. So we know by assumption of the definition of the model that the total variation distance between the ideal model and the observed model is going to be at most epsilon. And the goal is for this particular problem is to find a one-dimensional Gaussian that has total variation distance O of epsilon from the ideal model, or by triangle inequality, that has total variation distance O of epsilon from the observed model. So is the definition of the problem clear to everyone? Okay, so this is very similar to the definition of agnostic learning in the sort of pack learning of Boolean functions. Okay, so as Anoop said, the empirical mean and the empirical covariance fail miserably in this case, even for the one-dimensional setting. In particular, you just take a Gaussian, you add a little bit of noise very far away from the true mean, and the empirical mean is going to give you something arbitrarily bad. But this is not a problem. Statisticians have known this answer at least since the 60s. Instead of using the empirical mean, you can use the empirical median, and it's going to be as good as it could be up to constant factors. And there is something else also for the variance, for robustly estimating the variance. So there is something which is called an interquartile range, or something which is called median absolute deviation. And these things actually are easy closed form, essentially, solutions that work. So the folklore fact is that if we get samples from a distribution which is close, epsilon close in total variation distance to a one-dimensional Gaussian, then if we use as estimates the empirical median and the empirical MAD, then the total variation distance between our hypothesis and the truth is going to be O of epsilon. Okay, so we know this. So this is background. Now the question is, what happens in higher dimensions? So let me formally define the noise model I'm going to use for this talk. It is slightly stronger than the total variation distance model I just informally talked about. So consider the following process. So we have some family F of high dimensional distributions. This could be all spherical Gaussians or all Gaussians or all mixtures of Gaussians, some model that you like. And we do the following. We get n samples from an unknown distribution in the family, and then an adversary looks at those samples and arbitrarily corrupts an epsilon fraction of them. So the adversary is all-powerful, so they have infinite computational power, they can know what our algorithm potentially does. So this is the model, and what we actually observe is the corrupted set of samples, the set of samples after the adversary has corrupted an arbitrary epsilon fraction of them. Now note that here the adversary is adaptive, so he's allowed to actually look at the samples before adding or removing samples. The non-adaptive version of this adversary will be exactly what I said before, having sample access to some distribution f prime, which is epsilon close in total variation distance from a distribution in the model. And the difference between this type of setting and Huber's model, so essentially the model that Anoop talked about, is that the adversary can both add and subtract samples. And this makes a difference in algorithms. In fact, at the end, I might even mention that there is a provable separation between the two models. So is the model clear? So whenever I say an epsilon corrupted set of samples from some distribution, I really mean that the set of samples is constructed using this two-step process. Okay. And now the main problem that I'm going to study is learning an arbitrary d-dimensional Gaussian in this setting. So I get an epsilon corrupted set of samples from a d-dimensional Gaussian with a known mean and covariance matrix. And I want to efficiently compute parameters mu hat, sigma hat, such that the hypothesis that I'm going to get is going to be O of epsilon close in total variation distance to the truth. Something that I want to emphasize at this point, because it is crucial if you're not in this area, I'm not trying to estimate the mean of the covariance of the observed model. I'm trying to estimate the mean of the covariance of the good model before the corruptions took place. Estimating the mean and the covariance of the observed model is easy. Okay? Now there are two special cases for this generic problem. The first one, which in some sense captures the main ideas of our algorithms, is the case where we know that the covariance matrix is the identity, or it's known and fixed, and the mean is unknown, so we just want to robustly estimate the mean. And the second one is when the mean is known to be 0, but the covariance is arbitrary. So the case 1 captures really the main idea, and this is something I can actually explain during this talk. Case 2 is based on a similar idea, but it's somewhat more complicated. And now by putting together algorithms for 1 and 2 in a black box manner, we can actually solve the main problem. So for the unknown mean case, there has been lots of work on this problem. So this is exactly the same table that was shown in the previous talk. So I'm not going to go through this in too much detail, but the point of this slide is that prior to this recent work, there seemed to be some kind of trade-off between computational efficiency and robustness, in the sense that previous estimators were either hard to compute and provably robust, or easy to compute and very bad in terms of robustness. So they took an epsilon error in the input, in the robustness, and they gave an output error of epsilon times square root of the dimension. Oh, another difference, okay, with the previous talk is that I use epsilon for the fraction of corruptions, not eta. And D is going to be the dimension, not n. So I'm Greek, so if you give me an eta and an n in the same formula, there is no way I'm going to tell the difference after 10 minutes. Okay, so the main point, okay, the punchline is that previous estimators really required that there is a very, very small fraction of corruptions when the dimension is high. You really needed the epsilon to be less than 1 over root d for them to give you anything non-trivial. And so the question is, what can we do? And the answer is we can do something. So this is, let's say, the main result of this work with Kamath, Kane, Lee, Moitra, and Stewart. So let me parse the theorem. So there is an algorithm with the following behavior. So given epsilon, the fraction of corruptions, and an epsilon corrupted set of capital N samples drawn from a d-dimensional Gaussian M mu sigma, the algorithm writes in polynomial time in all the parameters, and finds some hypothesis parameters mu hat, sigma hat, such that the total variation distance between the truth, so this is the true Gaussian before the corruption took place, and the hypothesis is going to scale like this. So there is a term which depends on the error, okay? And so the form epsilon log 1 over epsilon. And there is another term that goes to 0 with the sample, Okay, so this is due to the sampling error, and this is due to the corruptions. So if we take the capital N here to be what you need so that the two terms are equal, we get as a corollary that if we use roughly d square over epsilon square samples, then we obtain a polynomial time algorithm that gives us a hypothesis at total variation distance epsilon log 1 over epsilon from the truth. So what's the contribution here? The contribution is that this term, the error term, is only a function of epsilon. The best thing you can do information theoretically, even if you take infinitely many samples, is epsilon, and we can get something which is comparable to that. It's completely dependent of the dimension. Now, in terms of like sample performance, this is a nearly sample optimal algorithm. So even without noise, d square over epsilon square samples are required to estimate the covariance. If we wanted to estimate the mean, and the covariance was known, the same theorem is going to give us a better sample size. It's going to give us d over epsilon squared, which again is best possible. So I'm going to go in more detail about this later. So is the main theorem clear? Okay, so let me move on. So simultaneous work by Lai, Rao, and Vempala has gotten comparable results. So Anoop talked about this, so I'm not going to focus too much about it. So let me now give you the recipe. So how do we do this? So I'm going to try to give you something which is structured, because really this recipe is what all our algorithms follow. So the first thing is to find some kind of distance between the parameters that is a good proxy to the total variation distance. So this is something that you need to do if you care about total variation distance. Okay, if you just care about L2, you just do L2. Now the second step and the third step go together. So what is our model? Our model is that there is an adversary that corrupts an epsilon fraction of the samples. Okay? Now it is possible that even though there are corruptions, the obvious estimators, which in this case is the empirical mean and the empirical covariance, actually work. Okay? It is quite possible that even though you have adversarial corruptions, they do not skew too much your empirical estimate. So we need to understand when they do, and then exploit that in order to be able to design an algorithm. So the algorithm is going to be an iterative greedy method that detects and removes outliers. So eventually, at the end of the day, we will remove all the outliers, or essentially all. I'm going to be clear about that. And we can actually output the obvious estimator for the cleaned up data set. So this is the approach, and let me be more concrete for the case of unknown mean. So I need to stand at a specific place that I can actually look at my slides. Okay. Goal number one, learn a Gaussian with unknown mean and identity covariance. So the first thing to do is to find the parameter distance. So this is easy. We know that if we have two Gaussians with different mean vectors and identity covariance, their total variation distance scales roughly as a Euclidean distance between their mean vectors. In fact, this is an upper bound, also a lower bound, if the distance between the means is small. So our goal really now becomes find an estimate nu hat for the true mean, such that the Euclidean distance between these two things is going to be O tilde of epsilon. This O tilde is hides some logarithmic factor, which in this case is going to be square root log 1 over epsilon as opposed to log. The log is something that we need for the case of the covariance. Okay, so how do we do this? Okay, here is the picture. I think this is the useful picture of the talk. So how does a spherical Gaussian, a Gaussian with identity covariance look like? Well, roughly speaking, it looks like a sphere, right? So you have a bunch of points that are at distance square root d, d is the dimension, from the true mean. So if this is like the true mean, it looks like a cloud of this form. Now in this picture, the black points are the points that are good samples, and the red points are points that the adversary has added. Okay? So if I didn't give you the colors, would you be able to tell me which are the black points and which are the red points? Varun?
Well, try and estimate the density.
So I just give you this picture, this cloud of points. All the points are roughly roughly concentrated like this. Can you tell me which ones are blue and which ones are red?
Not which, but maybe where.
Okay, so the point I'm trying to get to is that if there was a point which is here, okay, then certainly this is an obvious outlier. It's a point you can remove without thinking about it. Just looking at its distance from the other points, it should not be there. But the difficulty of high-dimensional outlier removal is that being an outlier is not a local property. It's a more global property of the data set. So you have to look at all the points in a global way to be able to remove outliers. So this is sort of a not well-defined statement, but I think it's quite useful because this is why people couldn't do this. Okay, so let's go back to the picture. So this is the true mean and this is the empirical mean. So we need to find some kind of certificates for why the true mean is far from the empirical mean. So this picture is constructed exactly for this. If this is the true mean, and this is the empirical mean, so the empirical mean is far from the true mean in this direction, what does this hint? That the red points cannot be uniformly distributed over the sphere. They have to be concentrated in some low-dimensional subspace, in particular in some particular direction. So this is the idea. More concretely, there is a direction that has large variance. Okay, variance bigger than 1. So we expect that if there is no noise, every direction is going to have variance about 1, since the samples come from an identity covariance Gaussian. So if there is a direction that has large empirical variance, it is a hint that something is going on in this direction. So the lemma, which is not difficult to show, says the following. So I get n samples. Sorry, I'm always pressing the wrong button here for some reason. So we have n samples, n epsilon corrupted samples, from n nu I, an identity covariance Gaussian with unknown mean, and n is large enough. Okay, at least something like dimension over epsilon squared. Then we look at the empirical mean and the empirical covariance of those things. So these are statistics we can observe. So the lemma says that with high probability, the Euclidean distance between the true mean, so this is the mean before the corruptions, and the empirical mean is going to be large only if the matrix sigma hat minus I, so empirical covariance minus identity, is going to have a large eigenvalue. Okay? So let's think about it for a sec. So what happens if there are no corruptions? Then sigma hat is going to converge to the identity matrix, because this is what it should have. So it will have certainly no non-trivial eigenvalues. And in this case, of course, we know that the empirical mean works. So a certificate that tells us that maybe the empirical mean is a bad estimate, is far from the true mean, is when the empirical covariance minus identity has a large eigenvalue. I'm not going to prove this. It's not difficult to prove. So let's see how we're going to use it for an algorithm. Okay, so the first thing to do is use the contrapositive. So just calculate the empirical mean, the empirical covariance, and find the approximate, the largest eigenvalue. If it is smaller than this quantity, then already we know by this lemma that the empirical mean works. And it gives us an estimate that's within distance epsilon root log over epsilon. We achieved our goal. So what do we do now? Like suppose that the empirical covariance has a large eigenvalue. What are we going to do? So the idea is that when this happens, then in some sense, the outliers, they need to have a special behavior in the corresponding direction. So in the direction of maximum variance. So the takeaway of this lemma is that the only way that the empirical mean, the first empirical moment, is going to be bad is if the structure of the second moment is corrupted in a detectable way. So let me go to the algorithm. So we call this filter algorithm. It's a spectral algorithm. It's an iterative spectral method to detect and remove outliers. So what does it do? So suppose that the highest eigenvalue is large. So we look at the corresponding direction. So the corresponding eigenvector, let's say unit eigenvector. So I claim that if you project your samples, your empirical data, which basically contains good points and corrupted points, in this direction, then the projection is going to look like this. Okay, and why is that? Well, the the big bump here corresponds to the actual Gaussian points. Okay, there is like a 1 minus epsilon fraction of the points are drawn from a Gaussian, so their projections are going to be Gaussian, so we're going to have something like that. And the small bump, which doesn't need to be exactly like this, basically corresponds to the noise. Okay? So roughly speaking, if I always get this, okay, if this is the direction of maximum variance, then these are going to be the projections. So all these points should be on this line. Okay, I just couldn't draw them like that. So these are the projections of the good points, and these are the projections of the bad points. The red ones are the noisy ones. So the claim is that there exists some reasonable threshold T above which there are significantly more red points than black points. So the reasonable thing to do here, and this is exactly what we do, that we find such a threshold T, and then we remove all the points of the data set that are above T. Okay, that's the algorithm, then we iterate. So let me state this a little bit more formally. So we have the direction of maximum variance. We project all the points in this direction. And then we find the threshold T that satisfies mathematically what I showed in the picture, in particular that the fraction of the points that in this direction are far from the corresponding median is larger than what it should be. Okay? And after we do that, we throw away all the points that are above, that violate this inequality, and we iterate on the new data set. So there are at least two things to prove here. One thing is that such a threshold point T that I claimed we can find exists. So why do you think such a point exists? Vitaly?
Sorry, I was acting out, but I think...
You've seen this talk at least twice.
Yeah, I see that. That's why I'm not following this.
No, but not by me, arguably, right? So it's okay. So okay, so it's like extremely simple. Okay, so we have the set S. This set S contains 1 minus epsilon fraction of Gaussian points, so going to be projections of high dimension, and epsilon fraction of corruptions. So certainly, if we were taking like the good points in S are going to satisfy this inequality, but the right-hand side is going to be less than e to the minus t squared over 2 because this is just the Gaussian concentration. Okay, we know that the one-dimensional projections of Gaussians are going to be concentrated around their median. Okay. Now the claim is that a significant fraction of the bad points cannot satisfy this inequality with less than or equal. Okay. And the reason for that is that it's by contradiction. That if the bad points actually satisfy this inequality with less than or equal for every value of the threshold T, then by definition of the variance in that direction would be small. And I am in a regime by assumption where this matrix has a large eigenvalue, and therefore the variance in this direction is large. So you just integrate, okay, this type of thing, and you get that the only way that the variance can be large if there exists a value of the threshold such that this is the case. Okay, and then clearly after you find such a point, the good points are going to satisfy this inequality with less than or equal, the bad points are going to satisfy this inequality with greater than or equal, you can throw away bad points. Now this is not enough because you can be unlucky. It is possible that some of the good points are going to be above the threshold. So in the picture that I showed here, we cannot really guarantee that there will be no black points above the threshold. You're going to have some bad points. On the other hand, this is not a big problem for the following reason, that the fraction of red points above the threshold is going to be at least twice the fraction of black points. Okay? And therefore, overall in this iteration, you're going to remove a very small fraction, less than epsilon fraction of good points from your data set across the iterations. And if you want to become a little bit more quantitative, so in every iteration, we're going to remove at least an epsilon over d fraction of the bad points, and at most half of that fraction of good points. So overall, after at most d iterations, we will have removed all bad points, and at most an epsilon fraction of the good points. We have a new clean data set, and we can actually estimate the empirical mean. Now, Of course, the algorithm might not work like that. Maybe in the third iteration, the spectral norm of the corresponding covariance matrix is going to be small, and therefore the algorithm terminates in that iteration. So there is one more thing we need for the analysis to be complete, and this thing is that, okay, I did all that. I have a data set at the end that contains no outliers, but I have removed potentially an epsilon fraction of good points from this data set. How do I know that the empirical mean of this data set is going to be good enough? So this is something that you need to prove. It's like easy for Gaussians, that if you remove any epsilon fraction of the good points, this cannot skew the empirical mean by more than epsilon square root log 1 over epsilon. So really subtracting a small fraction of the good points does not matter too much. Really the difficulty is in the added points. Okay, that's it. So are there any questions about this algorithm?
Yes.
Please.
So your lemma says that the deviation from the unit matrix is large, not that it's a right eigenvalue. It could be that it is too small eigenvalue, in which case your outliers are in the middle.
So okay, so we cannot have sort of this says that there's a large eigenvalue of this matrix, right? So.
It could be that it could be the direction of minimum variance has too low value.
Okay. So this is something we need to prove. So you never have a problem. You never have a problem with directions where the variance is less than 1. Okay. In particular, exactly for the same reason that I mentioned of subtracting points, the subtracted points can never reduce the variance by more than epsilon log 1 over epsilon. So really the points inside are not going to create a problem. So you only need to look at the directions of larger variance. Okay, yeah, this is an additional thing we need to we show. Okay. Okay, so that's the algorithm. So we iteratively do this greedy outlier removal procedure. After at most the iterations we terminate. So the sample complexity is going to be what it should be. It's going to be O tilde of d over epsilon square, which is the best thing you can hope for even without noise up to the logs. Basically this completes the analysis of this algorithm. So let me move on. So how much time do I have?
Still have 15 minutes.
15 minutes. Okay, I think it's enough. So let me say some things about how general this is. So the initial paper was written with a focus on Gaussian distributions and some other discrete families of distributions. The reason being that for these families, if you have a bound on the L2 distance between the means, then immediately you get a bound on total variation distance. But we observed after we wrote it that in fact it works much more generally, and we have written an experimental paper which pins down these guarantees. So if you have bounded moment conditions, then immediately we get something from the same algorithm. So the analysis is going to be slightly different because we don't have Gaussian concentration anymore. We have the concentration implied by the corresponding moment assumptions, but things are roughly the same. So if we only know that the covariance matrix is bounded, then we get an error of order of square root of epsilon, which is best possible under this assumption. If this is the only thing you know about your distribution, this is the best thing you can do. For your mean, for the second moment, we can get epsilon to the 3/4, which again is the best thing you can do under this assumption. And really, these algorithms for Gaussians, without any changes, they apply under sub-Gaussian assumptions, and they give the same guarantee. And as Anoop said, the sample complexity of all these different cases is not going to be d over epsilon squared, because there is no reason to estimate the empirical mean super well when you're only going to get a root epsilon error at the end. For example, for second moments, really d over epsilon samples are enough to get this type of guarantee. Okay, so that wraps it up for the mean. So let me say a little bit about the covariance, which is significantly more technical. And then I'm going to show you two pictures from our experimental paper. I don't have time to show you everything on the experiments. This would require another talk, but at least I'm going to show you something about synthetic data. So what do we do for covariance? So let's think what we did for the mean. So what did we do? We looked at the covariance matrix, which is the empirical second moment, and the highest eigenvalue, the spectrum of the covariance matrix tells us something about the empirical first moment. So roughly speaking, for the covariance, what we do is we look at the empirical fourth moment, and we use that moment to construct a filter to remove outliers. let me be a little more concrete. So the first thing, again, is to find an appropriate parameter distance for Gaussians with different covariance matrices. We're not going to use the Frobenius norm here because it is not quite enough when your Gaussians are skinny. So when your Gaussians are skinny, you need some stronger metric, which is called Mahalanobis distance. It's exactly this metric you have here. So the Frobenius norm between these two matrices, but don't worry too much about it. So the goal is to find an estimate sigma hat for sigma, so this is the true covariance, such that this is the case. So the Frobenius norm between these two matrices is small. So how do we do that? So the main goal, again, is to understand when the empirical covariance, which is this matrix, is compromised. And the key fact that we use in this case is that if you look at the fourth moment tensor of the xi's, where the xi's are Gaussians with zero mean and unknown covariance, then the fourth moment tensor is defined by sigma. I mean, there is a formula here which is not very enlightening if you haven't thought about this thing. So if you take this matrix M, which is like a d squared by d squared flattening of the fourth moment tensor, then you can show that the matrix M is exactly equal to this function of sigma. So this is Kronecker product, this is flattening. Okay, it's something, it doesn't matter exactly what it is. The point that M is defined by sigma. So now what we're going to do is we're going to take our samples, we're going to transform them by multiplying by the appropriate function of the empirical covariance matrix. And so these are yi's are going to be our, let's say, transformed samples. And we observe that if sigma hat was in fact the true covariance, then the yi's would be standard Gaussians. So zero mean identical covariances because of the multiplication I did, which implies that this matrix here, okay, again, don't look at it too much. It's like d squared by d squared matrix. It's exactly constructed by taking the previous formula from the previous slide, would converge to the zero matrix. Okay, therefore, without noise, this thing would have no large eigenvalues. So what we do is actually look at for large eigenvalues in this matrix. Now, this is a d squared by d squared matrix. What we did before was that the highest eigenvalue of the covariance matrix gave us a direction along which the outliers dominates. So here, the largest eigenvalue of this matrix and its corresponding eigenvector is going to give us a degree 2 polynomial that has larger variance under the noisy distribution versus n0i. And by using this degree 2 polynomial, we can actually construct a filter. So the details are quite elaborate, but this is the idea. Okay? Instead of using a linear form, a projection, to find outliers, I use an appropriate degree 2 polynomial. Okay, so this is the main takeaway. So to detect that the empirical second moment is corrupted, I need to look at the empirical fourth moment. Basically, that's it for the covariance. And if you have these two steps, if you have an algorithm that works for unknown mean and identical covariance, and another algorithm that works for zero mean and arbitrary covariance, you can assemble the full algorithm in a trivial way. Step one, just subtract samples to make the mean zero and use the algorithm for unknown covariance as zero mean. And then after you have an estimate for the covariance, you transform your samples and you reduce your problem to the unknown mean case. So this is like pretty much routine. So this completes the algorithm for the description of the algorithm for a general Gaussian. So what more can we do? So with the same techniques, but many more ideas, we're able to design robust algorithms for various other simple models, including models with hidden variables, in particular for discrete product distributions, for mixtures of product distributions, and for mixtures of spherical Gaussians. I want to emphasize spherical here because if they're not, we don't know how to do this yet. It requires fundamentally new ideas. And here are some experiments. So these are from an experimental paper we recently wrote describing the practical performance of those algorithms. So what is the main point? So we have actually implemented both our algorithm and compared against the algorithm of the previous work, so the LRV algorithm. So basically you can see here we apply a bunch of heuristics. In particular, Randstad is one of them. Geometric median is another one. Pruning, some kind of obvious outlier removal. You can see that all the previous estimators, they had a performance that deteriorates pretty badly with the dimension, while these two estimators of the previous paper and this one are essentially as close to the empirical mean without the corruptions as possible, okay? So this is again exactly the same setting as Anoop described. So we have an identical covariance Gaussian with a known mean plus 10% fraction of errors. And the similar picture is true for robustly estimating the covariance matrix. So really, these dimension-dependent factors of the previous are very real, at least on the data that we used, and these new algorithms actually do achieve dimension-independent errors. Okay, so this is I'm close to wrapping up. So what did I give you? I gave you algorithms for robustly learning various models, and in particular an arbitrary high-dimensional Gaussian that give you dimension-independent error guarantees and run in polynomial time. The first obvious question that a theorist would ask, there are a few in this room, is can you remove the logs? So we know that the information theoretic optimum to achieve for these problems is epsilon, or like a constant times epsilon. We achieve epsilon square root log for the mean, epsilon log for the variance. Can you remove the logs? So are there polynomial time algorithms that give you close to the information theoretic optimum? The answer is yes and no. So the no is that in the model that I described today, where the adversary can both add and subtract samples, there is a computational lower bound that I recently proved with Daniel and Alistair, which basically says that statistical algorithms cannot do this. So they do need super polynomial dependence on epsilon. And even the precise functions that we have in this paper, in this work, the epsilon root log for the mean and the epsilon log for the covariance, are the best things you can do. Any improvement on those, any asymptotic improvement would require super polynomial time. On the other hand, it is possible to get polynomial time algorithms with optimal error if you work in Hubert's model. If your adversary can only add corrupted points as opposed to subtracting corrupted points as well. So this is a very specific case to get the optimal answer for a Gaussian. Now, how about different, more general settings? So there has been lots of work by us and many other people in the past year on these problems. So this is like a sample of works I have seen recently. So I mean, I believe this is an area which is like full of theory problems and practically relevant questions. So I expect that in the next few years we're going to see much more on it. And at this point, I'm going to conclude.
So suppose you don't actually want to parameter learning, you just want to denoise. Is it clear that that's an easier problem than this? I mean, it might be for cases like mixture of Gaussians or something, like when you're not in a well-separated case or something, that parameter learning is just a hard problem. You might be able to denoise if that's
what do you mean by denoise exactly?
Let's say figure out what most of the outliers are.
I mean, if you do that, then immediately you can reduce to the case when there are no, there is no noise, and apply a known algorithm for the non-noisy case.
No, but suppose I don't actually want to learn the parameters of the mixture. I just want to basically figure out what the outliers are.
I mean, when you say easier, I mean, this is what we do. Okay, so basically we actually detect and remove the outliers that skew the empirical mean and the empirical covariance.
Yeah, but this is for a Gaussian, right? So if you have something like mixtures of Gaussians, does the same thing work?
Yes, so as I said, for the mean and the covariance, so the mean underlays second moment assumption, this method gives you the best you can hope for. It's like really surprising that the only model where what I described doesn't give you the optimal answer is for a Gaussian. It gives you epsilon root log, and this root log in some cases can be removed. If you have bounded moments, you actually get the information theoretically best possible thing using this technique. So roughly speaking, let me address this question a little bit more. So what we do is a reduction. Okay, we have like noisy data, and we have an efficient routine to reduce it to the case where there are no noisy data, roughly speaking. And then in the case where there are no noisy data, we can apply any estimator that works without noise.
possible to prove an adaptive upper bound that which would apply for adversaries that are not worst case, that was fairly nice adversary, he didn't perturb it that much, and the bound somehow automatically gives you, that doesn't give you the worst case epsilon, because
Okay, I don't fully understand the question. So I should say that the lower bound that we have here doesn't use the full adversary model. It works even for the case that you have samples from a distribution which is epsilon close in total variation distance. So the adversary doesn't need to be adaptive, doesn't need to have access to your samples for the lower bound to be true. Is this what you're asking? Or?
The adversary was nice and did something simple. Didn't do much, like just fooled around with point, didn't do much. Somehow your upper bounds still have would say less than equal to epsilon. So I'm saying, is it possible to prove an adaptive?
Oh, I see. Okay, I don't know how to prove. I don't know how to prove theorems about that. Certainly, there should be some nice definition that goes between, let's say, the worst case, where the adversary is all powerful, and the case where the adversary gives you a specific distribution that you also know, which I think is a little bit unrealistic. There should be something in the middle. But in practice, the experiments have shown that really these logs, square logs, are not real. Like even the square root log d that Anoop had, it doesn't seem to appear. So you really need to try very hard to. So there's some kind of difference between theory and practice. So these things seem to work better in practice than the theory predicts.
And the sample complexity with the filtering approach is d squared or d?
Which approach?
With the filtering approach?
So for the, it depends for which problem, okay? So for the Gaussian, it is d square for the covariance and it's d for the mean. So it's sample optimal for both cases. So in the initial paper, you might have seen, it's like a 120-page paper. We decided not to focus on these things, but in the experimental paper that we wrote recently, like a fine-tuning of the concentration stuff, like nothing super deep, gives you that these algorithms work with optimal sample complexity.
Any more questions? Okay, no more, then let's conclude.